Welcome to our talk on VersaMatch, ontology matching with weak supervision. My name is Jonathan Fürst, and this is joint work together with Mauricio Agarich and Bing Cheng. Let's get right into it. So as this is not something new for the attendees of this conference, data is constantly growing each year. However, much of this data is still siloed and not integrated. For example, it is existing in different companies or departments of different companies. And ontologies, as you can see here, like a source and target ontology, they can serve as a harmonized data presentation layer on top of existing data silos. They are widely used, for example, in the semantic web community, also in context of knowledge graphs, and more recently in the context of data sharing and data marketplaces. Ontology matching then aims to find correspondences, that means equivalent concepts across different ontologies. And this is important because many ontologies already exist and new ones are defined and extended over time, often in a decentralized way. And therefore, ontology matching at scale is crucial for data harmonization and integration across silos. Most ontology matching approaches currently use either heuristics or supervised machine learning. So we either need some set of label data to train a machine learning model, or we need to have a set of handcrafted heuristics or a definition of external knowledge in order to perform this matching tasks. And our goal with VersaMatch is to combine both these things, labels and external knowledge and heuristics, in order to train a model which then can perform this classification between match and non-matches between concepts of two different ontologies. In this, there are different set of challenges. First of all, we can see there's a lack of label data for training. Manual training requires extensive human effort, often needs to be done by domain experts. There are methods such as active learning, which can support labeling, but they also require usually a lot of manual user queries, for example, for related tasks such as entity matching. It has been shown requires around 1,000 user queries for achieving good performance. Second, there's the issue of limited flexibility to adapt to new data sets and domains. A lot of these existing matching heuristics and strategies, they need to be configured, for example, based on the ontology size or domain. And also many matches specialize on domains or baseline data sets, and they're unstable or provide limited performance of individual data sets or across domains. Third, there's a high imbalance between matches and non-matches in this context of ontology matching, which poses problems for machine learning, for supervised machine learning in terms of the feature lengths which we can provide, and in terms of generalizing to this long tail samples, to this long tail matches which we might have in this context. Fourth, we have the issue that there's quite a high complexity, such as in other matching tasks, we have O n times m combinations of class pairs. So let's see how we approach these challenges with VersaMatch. First, to give you an overview, we separate our method in two different phases. In the preparation phase, we enrich raw ontologies with additional information in the alignment profile construction step, and then create a subset of overall combinations of candidate combinations to improve efficiency in the min-hash LSH blocking step. In the matching phase, we perform weakly supervised labeling for combinations, and then perform a final prediction through a classification ensemble based on this weakly supervised labeling predictions of the label generator, and also a trained discriminative machine learning model, which has been trained by the labels created through weak supervision. So let's dive into it. First step, alignment profile construction. We do this mainly because ontology data is often quite feature poor. So you might just have a class name or a label and the hierarchy available in this ontology. So we enrich this with additional data to provide more input to the subsequent step of machine learning model training. For example, we get information about properties, neighbors in the ontology, synonyms, word stems, but also information from external knowledge bases such as Wikidata. Second, we present a adapted MinHash LSH blocking method for ontology matching. Just to recap, the general approach of MinHash LSH blocking is to compute MinHash signatures for classes in both ontologies, and then store the signatures for ontology A in a locality sensitive hashing index, for then being able to efficiently query similar signatures from ontology B. There's like two problems with that. First, we need to define a good similarity threshold for different combinations of data sets, for example, for small versus large ontologies. And also this method only represents lexical similarity and not semantic or structural similarity. And we solve this with these two things. First of all, in order to define a threshold, we exploit the fact that ontology matching is a constrained problem where at maximum we can find a number of matches, which is like the maximum number of classes in the smallest ontology which we have. And then based on our experiments and empirical evaluation, we find out that a threshold of 5 times this number is actually a good minimum threshold for the candidate combinations which should be returned by the blocking step. Second, to also encode semantic and structural information, we make use of the information contained in this alignment profile, where we have actually information about synonyms, we have structural information such as the neighbor classes in the ontology. Third, in weakly supervised labeling, we present a label generator which outputs probabilistic labeled data from these candidate combinations of class pairs based on this, again, on this alignment profile information. And we use a set of soft and hard labeling functions that encode supervision sources. The reason why we use these hard labeling functions is basically to be able to represent heuristics or also domain knowledge, which usually provides very precise outputs, but is very rare. So it provides only outputs for very few combinations, which cannot be implemented very well in a traditional generative model, such as used in Snorkel, for example, of a set of weak supervision functions. So in this, we either choose the hard output if it exists. For example, here on the top right, this function uses information of domain knowledge base. If this is not available, we use a traditional generative model using a set of the soft labeling functions. For example, on the left side here, we have a function which uses synonyms of this primary texts of the two classes. Fourth, we then use the output of this label generator to train a machine learning model. As I mentioned before, the issue is that we cannot have a very extensive, a very long feature vector. So we perform an optimal subset of features using recursive feature elimination based on ANOVA F values. You can see these features here on the right side of the slide. We also implemented different common machine learning algorithms. You can read more about this in the paper. It turns actually out one of the more traditional ones, random forest, is one which performs best in our data sets in our problem. Last, in the classification ensemble, our goal is then to get a single prediction based on the outputs of the label generator and also on the trained discriminative machine learning model, like the random forest model. And again, we combine this by either choosing, if there's like one of these hard outputs, we utilize this hard output. Otherwise, we use the output of a weighted ensemble, which contains the generative model, the label generator, but also the discriminative machine learning model. And the weight is computed based on the coverage, the model coverage of these labeling functions, and also the machine learning model for each data point. The benefit of this method is that it supports generalization through the discriminative machine learning model by sustaining high recall and precision at the same time. Last, I want to give you some interesting facts about our results, about our evaluation. So we perform an extensive evaluation using comparing our system to different form of matches. First, ontology matches, where we select 3 state-of-the-art matches: LogMap, AML, and YAM++. We also compare against 5 tabular schema matches out of the database community: Comma, Qubit, distribution-based, simple checkr, Levenstein matcher, and similarity flooding. Based on the implementation and valid time, we compare against 3 entity matchers: Magellan, LeapMatcher, and Dito. For all this, we compare in terms of precision, recall, and F1. This is like in terms of the overall evaluation, but then we also perform an appellation study where we evaluate the impact of different design decisions and components which we have in our overall design. We evaluate in 4 different data sets. 2 of them, Confluence Anatomy, are some long-running benchmark data sets of this ontology alignment evaluation initiative, which happens every year. The 2 other ones, Air Traffic and AI for EU, are more in the wild industry data sets. Also, the AI for EU has been part of some challenge at another conference. Looking at the label generator, we have overall 14 labeling functions. They average around 20 lines of code. What we can say is they're quite conservative in casting votes, which means many of them have only a coverage in the single digits, so they don't give a vote for most of the combinations. And here in this figure, we can see that actually adding knowledge sources has 2 different impacts. So it improves F1 and recall of the label generator gradually and consistently. But more importantly, maybe even it covers more combinations. So we can create more training data for the machine learning model. So this coverage increases from 0.02 to 0.37 in the end, as you can see here. Then in terms of the classification ensemble, we can see that the combination of this label generator and the discriminative machine learning model achieves the best performance in terms of F1 score and recall. So we actually gain 4 points compared to the best discriminative model, as you can see here, by still retaining the precision which we had before from the label generator for the points where the label generator did not abstain. Last, comparing it to the different baselines systems which I mentioned before, we can see that the VersaMatch achieves the best F1 score for 3 out of 4 datasets. For the anatomy dataset, where AML achieves a better score, we, however, can see that if we remove the implemented repair step of AML, we are achieving the best score with VersaMatch. And VersaMatch itself does not have a repair step after the final classification of matches and non-matches. So to give you a conclusion and kind of takeaways of our system, we can say that VersaMatch is the first system to adopt weak supervision to ontology matching. Also, our classification ensemble of weak supervision sources and machine learning model achieves generalization while retaining precision. And we achieve on average, as I mentioned, the last slide, a 4-point higher F1 score than state-of-the-art matching systems for 4 representative data sets. Also interesting to note, for this in the wild data sets, which have been not part of any of these challenges, we actually achieve a score 9 points ahead. Next steps, we want to apply our approach to other matching problems, such as entity matching, and also want to evaluate if you can use active learning to calibrate weak supervision sources and find additional matches. Thank you very much for your attention. Please feel free to ask questions via this email address, and the code and data is available on this repository. Thank you.